Now, in the previous section, we introduced the concept of multiple slits. Basically, when we saw the interference between two slits, we got basically a sine squared function. As we went to more slits, the constructive interference peaks became sharper and sharper. Eventually, when we got out to about 20 slits, we had extremely sharp peaks for constructive interference and very little intensity in between. Essentially, we reached the limit of the diffraction grating where the number of slits is large. So when we have these periodic boundaries, we can separate one wavelength of light from another, and this becomes a very important principle for things like spectrometer. So again, a diffraction grating has many equally spaced parallel slits. In fact, to create a diffraction grating, all you need is a repeating pattern. The intensity of the pattern on the screen, again, after it is passed through a diffraction grating or reflected off a diffraction grating, okay? The intensity pattern on the screen is a result of interference and diffraction that is taking place. That basically, where you have constructive interference, you get a very bright peak, and mostly, at most of the angles, you actually get destructive interference, which produces no light at all. So think about a diffraction grating again as a multi-slit mask, okay, where many of these sources are interfering with one another. So once again, we have our diffraction grating, and at the center of our pattern, we have a bright peak, okay? At some positive angle, we have our first order maximum, then we'll have a second order maximum, and then we have a first order maximum and the second order maximum underneath it. So again, think about a diffraction grating as, again, being this multi-slit obstruction where the distance between each of these slits is the same. It's going to be periodic in terms of where it blocks light and where it allows light through. We can create a diffraction grating very easily by taking some sort of opaque material and cutting very fine openings in it. The grooves are essentially just rectangular slits, and effectively, the place where we get constructive interference satisfies this equation right here. D, which is the distance between the slits, times sine theta is equal to m lambda. M is the order, so m can be 0, or it can be some positive or negative integer. Lambda, of course, is the wavelength of light. So what we see here is for different wavelengths of light, our constructive interference is going to occur at different angles. If we know the angle at which the light is diffracted, and we know the distance between the slits, we can calculate the wavelength of the light, which is at that particular angle. So again, going back, here's our single slit diffraction pattern. Here's our double slit diffraction pattern. We can see how these interference peaks are getting more and more narrow and more distinct, okay? And again, we do have to account for diffraction. This is our first diffraction dark fringe. Here's our diffraction dark fringe. So that is really due to the width of each of these openings. In this case, this was laser light sent through a 50 micron opening, okay? And the distance between the slits was 150 microns. So our interference pattern is smaller than our diffraction pattern because, again, the distance between the slits is greater than the width of each individual slit. But again, as we add more and more sources, constructive interference will happen for a narrower and narrower range of wavelengths. And basically, we can again see for a single wavelength that our central peak right here will actually be more intense, okay? This is not accounting for the difference which is due to larger and larger angles. But again, we can see the first order, the second order, and so on. What if I send through 4 different wavelengths? A red, a yellow, a green, and a blue. Red maybe at 650 nanometers, yellow maybe at 580 nanometers, green about 500 nanometers, and blue, violet, about 450 nanometers. Well, again, sine theta is equal to m lambda over d. If the wavelength is smaller, the angle is smaller. And clearly we can see that the violet light comes out at the smallest angle. Then green light, slightly larger wavelength, now around 500 nanometers. Yellow light, about, again, I said 580. I'm trying to think of sodium light. And then red, again, 650 nanometers. So the first order we can see is spread out like this. Then we get to the second order, and effectively in the small angle, sine theta is approximately equal to theta. If I double the order number, okay, for the same wavelength, I'm going to have twice the angle. So here's my first order. The second order is at twice that angle. The third order is at 3 times that angle. And you can see how these lines spread out. So if I wanted to make this into a spectrometer, okay, all wavelengths of light are going to have a maximum at the center where the angle is 0. So that doesn't really help me separate the wavelengths. But at each higher order, m equals 1, m equals 2, and so on, the position of the wavelength is going to depend on the order number, obviously, but also the distance between the gratings and where that wavelength is. So again, the old way to make a spectrometer was to put light through a prism and use dispersion to spread it out. This way, we can send the light through this diffraction grating, not worry that the glass might absorb at wavelengths in the infrared or the ultraviolet, because glass is not all that transparent as we get away from the visible. And I could create a spectrometer to essentially evaluate just about any type of electromagnetic wave under the right conditions. So again, here is a transmission grating. All the slits are equally spaced. All the slits have an equal width. And if I put white light through it, the white light is going to produce a maximum at the center. But notice what happens to the white light. This is a continuous spectrum, with the first order, the second order, and so on. All right? The angle at which the light is diffracted, this is actually the opposite of what we see with a prism. The shortest wavelength light is diffracted the least. The longest wavelength is diffracted the most. A more efficient way of creating a spectrometer is to use a reflective diffraction grating rather than a transmission grating. After all, if you think about a transmission grating, these are openings in an obstruction. So I'm blocking some of the light that is coming through, okay? Maybe I'm blocking 50%. So if I have a very dim source of light and I want to break down its spectrum, it's going to be a little bit difficult because I've lost 50% of the light. If I use a reflection grating, then essentially I'm nearly reflecting all the energy incident on this. Now, in fact, we can make a diffraction grating even more efficient than just a simple take a surface, etch different lines on it, all right, and then coat a reflective surface on it. The problem here is I'm going to be sending energy at all these different orders. If instead, here's an old CD, by the way, which actually acts like a diffraction grating because you have these microscopic grooves at which a laser beam will reflect off of. We see this with the old CDs, by the way. We don't see it with the DVDs because the DVDs, actually, the grooves are too small. They're much smaller than what we get on the older CDs. Okay, so going back to making our reflective grating more efficient. How do we do that? One way to do this is to create a diffraction grating. Now, before I could create a reflective diffraction grating by just cutting grooves in this, much like we have on an old CD, okay? But the best way to do it would be to actually angle the surface such that, let's say, the first order is most strongly reflected, okay? Again, if I don't have any preference right here, most of my energy is actually going to be diffracted at the 0th order. We'll have less energy at the first order and even less energy at the second order. But if I bias this a little bit, we call this a blazed grating. I bias it so each of these microscopic surfaces are almost like little mirrors. If they're going to reflect strongest in one particular direction, in the direction that my first order goes, okay, then I'm going to get a higher efficiency. Okay, here we can see a blazed grating, and we have incident light coming in, it's white light, all right? And you can see the 0th order right here. The first order right here matches the angle at which the has been set up so that the blaze angle of this reflects the m equals -1, the strongest, and the other orders don't have as much energy there. So this is one way to, again, sort of bias the system is really what you're doing, so that we have more energy sent in one particular direction, and I get, especially for very dim sources, I get as much energy in that direction as possible. And this is what a diffraction grating spectrometer would look like. The beauty of this is you can create a diffraction grating for the infrared. You can create a diffraction grating for ultraviolet. As long as you have a reflective surface at that particular wavelength, this will work. You can't do that with a prism spectrometer. So we send our light through this slit. It is then sent to a collimating mirror, which is just a parabolic reflector right here, a concave reflector. It is going to, as the name implies, take this light that is spreading out and collimate it. So basically we have plane waves hitting the diffraction grating. They are going to send the light in the first order to another collimating mirror, and then that collimating mirror is going to send it to a detector. And the detector can be a movable detector, it can be an array, but basically it will count how much energy is contained at each individual wavelength, and then that can be displayed as a spectrum. And again, this is a very, very important instrument in astronomy, very important instrument in chemistry, any place where you want to find the energies, you want to find the wavelengths that are being given off by a particular sample. Here's a beautiful example of where nature has beat us to the punch. This is a blue morpho butterfly. These are found in South America, but we have other examples here where other animals also exhibit this type of color display. Now, most organisms will demonstrate color due to selective absorption. So for instance, if something is red, typically it's absorbing the blue and the green wavelengths. This is what's called structural coloration. This blue morpho butterfly has no blue pigment. In fact, the pigment in it is actually brown. It absorbs all colors. So structural coloration, since blue pigment is very difficult to make, can be achieved by taking these microstructures, effectively small diffraction gratings, and only diffracting certain wavelengths of light. It's more complicated than our diffraction grating, because our diffraction grating will just, show us all different colors. Here, it will diffract the blue light at a particular angle where it can escape the microstructures, and we see this as blue to our eyes. So There's nothing, in terms of pigment that is causing this. It's purely a diffraction effect that is creating what we're seeing, okay? Peacocks do the same thing. If you've ever seen the coloration on a peacock, you notice that it's typically blues and greens. So the microstructures in its feathers are of different sizes and different geometries. And again, here you see a different butterfly, and we can see this iridescence where it's showing more green up here and more blue here. Bluebirds, same thing. Blue jays, all of these animals, because blue pigment's very, very difficult to create in nature. These are structural type of coloring that is due to these tiny little microstructures. Here is a electron microscope view of one of these microstructures. And we can see here that they are on the scale of less than a micron. They're on the scale of nanometers. They're on the scale of light. And again, in this particular case, not only will it diffract light, but it will selectively trap all but the blue light. So what do you see? You see blue light there.